Cool. Okay, yeah, then I'll get started. Yeah, so I guess quick introduction. I'm Corbin. I work over at Leviathan Security Group. I like coffee a lot. And I've got a nice mechanical keyboard, my favorite color scheme. Miami's the best color scheme. Yeah, and I guess I'll start off with a little talk on, I guess, what I'm going to be talking about, and then we'll go into it. And be switching back and forth between VM and slides.
Hey, Dwayne. Come on in.
So, I guess one of the first things when I work on an engagement or anything is to kind of get fuzzers going. And the first rule of fuzzing is always be fuzzing. And I just wanted to get something quick and dirty running. So I wrote this really ugly bash for loop where I thought I would just iterate through a bunch of stuff. And I don't remember what tool I was using, but I had I being saved over to the disk if the exit case was not successful, because that's an interesting output. That way I could come back later and just be like, okay, which iteration failed, and go back and look at it. And, oh man, I'm not in bash. Yeah, and copy. And one thing that uh-oh, bash. Yeah. Yes, and one thing I noticed a typo when I was running this, and so obviously I just sent an interrupt, and it has to take a long time. I was like, huh, that's funny. That shouldn't be happening. Except it was actually more annoying because I was on SSH and it was a very slow connection, and so I just thought maybe my connection just keeps dying. Except I was like, wait, my screen session just died too. So I had to go figure out what was, yes?
I'm sorry, I don't see the typo. I'm not.
Oh, sorry, there's no typo in this. This is when I was, this is just, I could have put a fake typo in there. Yeah, I had a typo in my code when I was actually running it. I'm not going to rewrite my ugly one-liners, probably like 20 semicolons. Yeah, and so yeah, I just Control-C'd it to go fix the typo. There's no typo in this one though. And I eventually figured out that it was bash itself crashing, and I was like, that does not happen. So I guess at that point I decided I'd try to go figure out what was going on, because crashes are always interesting. So I brought it home, and I realized that it was occurring specifically when I called an interrupt during a brace expansion, which brace expansion is that curly brace thing. So the question is, what's happening under the hood for this brace expansion, and can I figure out if this is actually like, could it be an integer overflow or buffer overflow, or what kind of vulnerability is this? As a quick how the brace expansion works, because a lot of people don't seem to know about this in bash, but it's pretty helpful, is that you can just do curly braces and do a start ... end, and it will iterate the whole thing. So you can use integers and characters, and it's kind of like a for blank in range in Python is kind of what I've been using this for. And some examples, if you echo 5 to 12, it'll print that out. C to K, it'll print that out. You can even put characters or strings before or after the brackets, and it'll append it to your character. That's pretty helpful. Yeah, so sadly, I noticed that the bash man page said that it doesn't apply any syntactic interpretation to the bash expression. It just expands the text. So it's not a parsing issue, most likely, and that probably means I didn't know what kind of vulnerability that could have been. And before how we went into debugging it, I'll give a quick primer on Heap Basics, just in case people here aren't familiar with memory corruption in the heap. and I drew some nice graphics to help with this. So here's the classic process memory model, where you got kernel and stack up in the high address spaces. You've got your binary text segment and your heap down there. Heap grows up, stack grows down, and there's more than this, but this is pretty much everything we care about. Specifically, we're only caring about the heap. So we'll look at it as it makes a couple allocations. So this is also super simplified, but essentially heap starts growing up. So as you make allocations, it'll start from the bottom and it will continue to grow upwards. The allocations can be variable sized. It's basically however big you stick to malloc. Yeah, and you can keep growing. If you free memory, it can be removed. And after you free memory, if you make a new allocation, if it's small enough, it'll fill in the gap where the old memory was. If it's not small enough, it'll keep going from the top. And that's sort of the 101 for heap if you have not played around with it too much. And as a quick disclaimer, I have not read through all of this code in detail, so if someone actually is an expert on bash and I make a small mistake, this is all based on things I identified via GDB. I did not do a code review of the brace function, so sorry if some assumption is incorrect. So the way that brace expansion works is, let's say you have this 0 to 5 that it called out here. So the way that it fills this out is it first creates space for an array of 6 car stars, car pointers, and it'll create a string, whatever string it needs to, and point at it. So if you remember, this is going to print out the strings 0, 1, 2, 3, 4, 5. So the first entry will be 0, and it'll fill out the rest of them as it goes. So it's an array to 6 strings now. And as I stated earlier, the crash is occurring when I'm hitting Control-C, which is a interrupt signal. So it wasn't too bad to try to go find when the interrupt signal is called in the code, where is that occurring? So I did exactly that, and it very nicely, if the interrupt signal is called, I found this code that says it's going to dispose result. And result is that array that was down here at the bottom. So it's going to dispose result, and the dispose function checks if the array is valid, and if it is, it's going to flush it. And the flush command is just going to check if the array is valid again. And the way they do their freeing is they go from I equals 0, the beginning of the array, up until the array is null. And they're going to free that element in the array. So I guess the question is, or I guess I'll show visually in case, because see code in slides is always unfun. Visually, it goes, so the first thing it'll start at 0, which is the 0th, or the 0th entry is 0 string, and it'll free that. And then it'll free 1, 2, 3, 4, 5, and then at the end it frees the entire array itself. So pretty straightforward way of doing it. However, what's happening when I'm hitting Control-C is that the array looks like this. If I send an interrupt signal after, let's say, only the 0, so the array has built up to this, only the 0 string, and I hit Control-C, now it's going to send that same command to try to free all the memory. And what's going to happen when it hits this red part, which is unallocated memory? Using bash malloc, which apparently bash has its own malloc that they wrote for some systems. I'm not sure how many systems use it, but anyone using that, it's pretty straightforward that they use this mem scrambling where when they allocate memory, they set every value to 0xdf. So this red space for any system using bash's malloc will just be a bunch of 0xdfs. The more interesting question is what's happening if we're not using bash malloc, if we're using the system malloc instead. This is known as stale memory, and stale memory is kind of undefined. It's undefined, so it's whatever was in that address previously. So what I mean by that is, let's say there was an array there before, those same values from that old array will still be there. It's whatever was there, it's the stale values. And as an attacker, what we want to know in this scenario is, can we somehow control those stale values that are being used for control flow execution? And this really is application dependent and even function dependent. However, in this exact bug, it should be possible via a technique called heap spraying. And Wikipedia can explain heap spraying better than me in big words. That basically heap spraying is you're going to be allocating a sequence of bytes in order to try to allocate target areas and try to fill it with the right values. And essentially, we have this red spot, and we want to cause a spray of values to fill up this location. So you can think of, for instance, a common thing is to create a giant string that's a gigabyte long of not random data, but controlled data. It has to fit that gigabyte of data somewhere on the stack, and now you have all those values there after you free them. And there's techniques to do sprays at like specific times to try to time it so that you can fill up that slot. If you remember, when you free memory and there's that gap there, then the allocator might actually put that new memory inside that empty spot. So we'll talk about how we might do a heap spray in this situation. So we know we can execute as many commands in bash as we want before triggering the bug. So I can, because in order to cause this signal interrupt with the brace expansion, you already have to be at the bash prompt. So presumably you can execute however many commands you want in bash before triggering the bug. When the bug is triggered, each value in that stale memory is going to be assumed to be an address that it'll try to free. It'll think it's pointing to somewhere in memory. So if it's 0xdf, df, 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 like the bash malloc, it'll actually try to free at the address 0xdf, df, df, df. So what the attacker wants to do is try to make that address something interesting that he knows. And finally, we know that when the address read is 0x0, the array is assumed to be freed, and it'll stop trying to free more memory. Yes?
Bash team ever explain why they're filling with df instead of nulls?
Security reasons, which is why it prevents this issue from occurring. Yeah.
Is df a guard page or something? Yeah.
They just, whenever, they call it memory scrambling, and every time that it allocates new memory, it just sets every byte value to 0xdf.
Yeah, but I mean, like, is that on a guard page that's been specifically reserved as unallocated, so it's always going to fault if it tries to read from there, or?
Actually, I haven't tested it too thoroughly. In this case, it did, because it was inside this red space. All these values were dfs. It actually was trying to free the address df. So df's going to be in kernel memory space since it's in a high enough address range.
This is why filled with nulls
yeah.
is common, because the
Yep.
null page is full of nulls and you can't do anything.
Yep.
On the flip side, a pattern like that is often used for debugging, so you know if,
Yep.
so you know, like, this is
Yeah.
definitely uninitialized memory.
Yeah, they had some note that
Just happens to have 0 written there.
they did have some note that it was for debugging purposes, and that's. I assume they picked df because it's gonna. They use df when they allocate, and they actually use cf when they free. So everything they're freeing, they fill up with cf. Yes.
Except for being high addresses, are they arbitrary? They could be AF, BF, or...
They specifically use df.
They specifically do, but is that an arbitrary choice
They
they've
probably
Yes,
have
that's
the code
arbitrary
that's
choice they-
detecting the CFs and DFs so they can debug itself.
Yep, exactly. Yep.
Did your target have unscramble turned on?
Yes. Well, actually, the machine I was originally using did not have the bash allocator. But like when I compiled this, because when I was debugging it for the first time, the default compilation has memscramble turned on. And so I was hitting the DFs when I was trying to debug it myself, which
Remember-
actually made it a lot
remember
easier.
corruption bugs are not stable when you replace your mallocator.
Yeah. Except it's more stable in this case. Yeah. Yes.
As an interesting historical note, IBM in their AIX used dead beef, which there was part of the people who did it were out of the Austin office. So they filled their memory with dead beef when they run their allocator.
Yeah.
So for debugging, so they could tell the difference between when the system had allocated it versus it had been used by somebody else.
Yeah. So I just see a lot to that and like cafe and all that stuff. But yeah, going back, yeah, and when it reads null, it assumes the array is finished being freed. So now we know a heap spray pattern that we want is that we can now have a list of addresses that we want the program to free, and then we can just end it with the value null. So when we trigger our bug, if it starts at the beginning of our heap spray, it will read off our addresses and one at a time, free the values of these addresses, and then read null, and then finish. And the way you would do your heap spray is you would take your pattern that you want, and you just repeat it a bunch of times over and over again, and hope that probabilistically it will land near the beginning of your heap spray. The problem with this is, as you know, with this bug, you have to send the interrupt signal. It is very difficult to time it at the exact point in time that you know how far it's built up the array. Like, it could be 936, it could be 827. Like, I don't know of any way you could practically time this bug to be exact. So that's why you would need to use a heap spray in order to be able to control, have any chance of control over which addresses are being freed.
Were you manually figuring these out?
You have,
Can you script that?
you could script it, but even still, it's gonna.
It's not gonna be
yeah,
precise.
yeah.
I get that.
Yeah, you can make it more precise if you scripted it, like, yeah. But yeah, I just was manually triggering it. Yeah. So now, if you're not familiar with this kind of exploitation, why is a controlled free useful? This is actually, could be used for a type of bug that's called a use after free. And the way that this bug works is, say in memory you have a function pointer. If you free this value and then can reallocate it over it with an attacker controlled value, then later on when it's called, you could cause attacker control code to be executed. So my little example here is, say there's a function pointer somewhere for pointing at the address 0x_deadbeef. If you use this controlled free to free this function pointer from memory, and then you use, let's say, like another heap spray to just shoot 0C, 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 0C everywhere over memory, you might be able to fill it up with that value. And the next time that it tries to call this function pointer, it'll instead call the value at 0C, 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 0C in its place. And this could be used to hijack control flow from a program. And there's all kinds of complicated ways where function pointers show up, like C++ objects being an example of one. But yeah, the problem is in this case, oops. Yeah, the problem is in this case, we're in bash. There's not really anything interesting you can do with control flow execution, because one of the first common things you do when you exploit something is you open up bash. So the question is this bug actually interesting at all, since you can already do pretty much anything anyways. And a use case where it might be interesting is if you have a restricted CLI, like think routers or something. Brace expansion might be enabled, but they restrict a subset of commands. So this might allow you to break out of a restricted CLI. But I was having problems finding anything really interesting. Yep.
Another scenario would be if you had a set utility shell script.
Yeah.
Then this could be Prevesc.
Yeah, that could be too. I'm trying to think of how you'd stick a brace expansion. I guess you have
Well,
to
if the shell
command
script had
yeah.
brace expansion in it,
Yep, that's true.
then you would trigger in the middle of the brace expansion,
Yeah,
and then you'd be able to take over its process that's running as root.
yeah.
That feels like that would be slightly harder on the timing too, JavaScript gets to them.
Yes,
Yeah.
but it's an actual privileged scenario
Yeah.
as opposed to attacking yourself.
Yeah, that's true. Yeah, and the only restricted tool I could find that was based on Bash that had brace expansion, like I was trying to find open source ones because I thought maybe it'd be a fun demo to try to break out of some open source thing, but the only one I could find was like OpenConfigD, and it looked like too much of a mess to install because it's like a whole other system on top of it. There was an easy, yeah.
Isn't giving like guess if you have SSH access just an RBash instance a pretty normal thing probably?
Yeah,
You see that in CTFs.
yeah, the problem with RBash is there's easier ways to
Oh,
get
there's
it.
just easy bugs, okay.
Yeah, I feel like trying to find a bug in Bash might not be the easiest way. Like the trivial thing is if they forget to chroot you, and you can just run bin bash without being restricted. Like it's really scenario dependent on how they configure their RBash. RBash by itself is not meant as a security thing on its own. You have to do a lot of configuration around that. Yeah. I ended up thinking that the most interesting thing for this talk, though, would be using read-only environment variables. And I actually don't know if these are intended for security usage as well, because there's a lot of weird things in Bash that seem like they're kind of meant for security, but they end up being bypassed fairly easily, and then they come back and say this isn't meant for security. But I couldn't find anything online really talking about how to bypass read-only environment variables, short of some Stack Overflow page where people said attach to your own process with GDB, and then you can unset it. But there's a lot of systems where you can't GDB your own process because your kernel can actually disable that with blanking on the flag name, somewhere in like syskernel ptrace something or other. You can require root access to attach GDB. So this essentially is a way to modify a read-only environment variable without needing the privilege escalation with GDB. So as an example of read-only, you can export a variable and then mark it as read-only. It'll refuse to let you write to this variable again, yelling at you that it's read-only, and you can't unset it either. Also yells at you that it's read-only. And so we're going to use this bug to overwrite this read-only environment variable to something that we want. And an example where this might be bad is, let's say you have like a external script that relies on an environment variable being set in order to reach out to a server. So they hard code a server into an environment variable and pass that in, and you can overwrite this variable now to connect to maliciousserver.com or whichever TLD you wish. I'm sure there's other uses as well. So an interesting note is that with a bit of playing around, I learned that Bash is deterministic enough that environment variables and things inside Bash RC are actually located at completely deterministic addresses. So with ASLR disabled, it's at the same exact address every time you start. With ASLR disabled, it's going to be at the same offset from the heap. And you can actually, I'll show that in the demo. That's in a couple slides.
Is address randomization disabled by default, or it just
No.
depends on the distribution? Okay.
It'll be in, or it depends on the distribution, but pretty much, I don't think I've ran into a system with ASLR turned off by default recently, except for older things. Yes, and so what we would need to do for this bug now to overwrite this environment variable is heap spray a repeating pattern of the address to the environment variable followed by 0. Then trigger that controlled free, which will free that address to the environment variable. And then we can heap spray that new string we want in its place and hope that it overwrites that address where the environment variable used to be. And hopefully it's overwritten at that point. And I did not have time to completely finish the proof of concept. I'm sorry. I've been kind of busy this month, but I will show you what I have in proof of concept state. So, Oh yeah, so I'll actually first show that the environment variable is going to be stored at a deterministic address, just because I feel like that's kind of important. So the way you can check that is, I'll just open up bash. And I will connect to bash with GDB 303. So what I'm doing here is we're interested in the heap, which is in these addresses. So to find where this environment variable is stored, I'm going to use pwd because it's very simple to find. So if I echo pwd, this is the value. Oops. And I can do a find at should have made this copy and paste, my bad. The next one will be copy and pasted, so I won't have to do this again. I think that's it. 80C. Uh-oh. We'll just do that. Now you can see if I echo it again, it is now the value A because I overwrote that memory address. And you can see it was stored at this 6F, wait, I'll read over here, the 67F948. So we'll kill the process. Open it again. And we'll do the same thing where we set that same address to A. 41 hex is A, if you weren't aware. And you can see it's at the same address again. So we know this environment variable is always stored at the same address since I closed it and opened it up again. Now the bug itself, oops. So as I said, I couldn't finish the proof of concept quite in time, and I will be straight up with the place I cheated in that. Man, this VM is going terribly slow. Is I just hard-coded the address of what the heap spray should have been spraying here. Presumably, you can find a heap spray that would actually write this, but I was having issues getting something allocated where that array was, since there's not a lot of things in Bash that let you store allocations over a large chunk of memory without being freed shortly thereafter. Since by the time I'm hitting this interrupt signal, I'm getting like 350,000 elements into the array or something ridiculously large like that. And so I would need my heap spray to reach that many values of controlled space before I could reach where that free is occurring. So that's sort of why I just, for now, put it in there. And I guess it's an exercise to the reader to try to find a real heap spray here. But yes, other than that, it is pretty easy. I can just caused the bug. Oh, I forgot to actually set the variable as read-only. That's an important part of the demo. So echo, I'll do pwd. I'll set pwd as read-only. And now, just as a, you can't overwrite it, you can't unset it. Oh man. And this takes a few tries because I don't really have a good control over where it's being allocated, and I kind of just have to get lucky. But I have a window open in case this demo doesn't work after too many tries, or I did it earlier. But usually it ends up working within like 1 in 10 tries. Dang. I don't think it does. It's entirely possible it does, but I don't think it does. We'll try it just once. I wish it was faster to control C too. Oh, there we go. And now you can see PWD is now not what it was before. And it's still set as read-only. So it is overwritten. Oh, now it's even worse.
That's cool.
Yes, now it's like completely broken. But yeah, as I said, I kind of had to cheat in that I did force the heap spray, but heap spray should be possible. I just need to play around with how to do more controlled allocations in Bash, and it's kind of difficult. Yeah, hacking is hard. Yeah, so. I can't give a talk on a bug without talking how to fix the bug. And you can fix this bug with 1 line of code by signaling in this interrupt signal that this is the last element by setting it to null. So then that value that checks to see when it is null is actually at the correct point in time. And I already sent this to the Bash development team, and there's like a little write-up on their mailing list I did of how I debugged it with GDB and everything. And they actually pushed the patch within 30 minutes of me sending it into them. I was like, that's really fast. So yeah, they're super helpful. Yeah, this is kind of a limited use case bug, but I thought it was a straightforward representation of use after freeze, since a lot of the times they rely on really funky C++ antics or that kind of stuff. And yeah, that's pretty much it for this. If anyone has any questions. Not yet. I plan to. As I said, I've been busy this past month. I haven't even had time to finish this. Yeah.
UAFs are a little bit broad.
Yeah.
UAFs are everywhere. So you made fat bank on this? You're driving around in a Porsche and stuff, you know, when you disclosed it
Oh,
responsibly?
it's not that useful of a bug.
You didn't do it right.
Yeah.
Anyway, cool. Are there any questions? Anybody?
Yeah.
Did they give a CVE for the bug? It's obviously memory corruption.
I'm gonna wait until I have a provable, like, full proof of concept, because as I said, like, a bug in Bash isn't really that. It's not the same. Like, you already can execute arbitrary commands. So unless I can get a provable privilege escalation, I don't really think it's
CVE is for exploitable bugs, not just oops.
Just
Yeah.
a toy bug.
I think it's exploitable somewhere though, so I'll go find some like toy CLI or something. Yeah.
Cool. Is that it?
Yep, that's it.
All right. Well, thank you, Corbin, for lighting up. I don't know if there are any questions on YouTube, but you know, if they did, you know, how would people get a hold of you if they wanted to ask you more questions about this,
I wanted to work with you.
or wanted to work? Oh, you don't want one?
No, man, yeah. I don't have my name anywhere on here.
I know.
This is being streamed to YouTube, so I'll just add it to.
So, this bug, is this bug already publicly known, or is it embargoed by the Bash people?
Oh, it's publicly known, yeah. They, as I said, like, it's not really a bug in bash unless there's a useful thing. Like, you can already do commands that do basically everything in here except for overwriting memory, which they claim overwriting memory is not really anything that useful for a user, but as you can see, there's like some scenarios where it is, but they say it's more of people using bash in weird ways, not the bash application itself that has the bug, which makes sense. Yeah. Yeah, it's on their mailing list too. If you Google like use after free bug in bash from, I reported it last month, I think, and it's all on there. Oh yeah, and I need to add that.
Does everybody have a ticket? Everybody have a ticket?
I guess for people.
Corbin, what is your role at Leviathan? Do you hunt bugs all day, or what?
Yes.
What do you do?
I am a security consultant, and I do everything. My prior background was all in like automated binary analysis. Sort of here, I've been shifting more towards like firmware level-oriented gigs, but I have done everything from like, I've looked at a rootkit for a client. I've done web app development stuff, or not, sorry, web app review stuff, crypto review. I'm looking at hardware right now, just all over the place. Mostly firmware and binaries is probably where I sit though. Yeah. Yep.
Not really a question, more of a story. The Microsoft Edge team implemented an interesting defense against UAF. They called it an MGC, where basically you call free and it's a NOP. It doesn't do anything.
Yeah, and they have the
Doesn't actually free it, and instead they implemented a garbage collector that reference counts all the memories and only really frees it when all the references have gone away. And you cannot have a UAF if you don't free it. So that dramatically reduced the huge farm of UAFs that the browser had.
Yeah, and there's been some other interesting things too by both browser teams and like I know Flash upped its mitigations a few years back. And that, for instance, other techniques are they use what's called like segregated or isolated heaps. So they have these common heap spray vectors, as I said, strings where people hide things in, and they actually have two different heaps, like really far apart from each other in memory. So all those strings and stuff that are usually used for heap sprays are stored in completely.
They separated the things that can be used to corrupt pointers from the things that can contain code buffers. So that the one can't point at the other.
Yep. And other things I've seen are there's like delayed freeze where they'll say we'll have 100 frees occur, we'll say, before we actually free it. We'll just store a circular list of the past 100 frees and keep going. That way, in order to get this kind of use after free to occur, you need to like sit on it for a while and then try to get your allocation. But at that point in time, the application's probably filled up that space and crashed itself in a non-malicious way. Is their thought for that.
Hacking is a lot like building a ship in a bottle, and that technique is making the neck smaller.
Yeah.
Cool. All right, that was it. So yeah, thanks for coming. He's